So for those of you who don't know who I am, I'm Alice, and today I'm going to talk about the mass assembly of the Milky Way halo. Right, so in the field of galactic archaeology, one of the main things we want to understand is how our Milky Way assembled, what were all the little fragments that came in to our galaxy over time, and how did these accretion events happen? And it's really only in our galaxy that we can understand these processes in exquisite detail, really star by star, find out all the things that have happened over time in our galaxy's formation. So we have very strong predictions from Lambda CDM what the type of fragments are that we should expect in terms of dark matter. Okay, we can go to our favorite dark matter early simulation and understand what kind of mass spectrum of dark matter we should expect to be accreted onto a Milky Way mass halo. For stars, it's a bit more trickier. Okay, how do we understand the stellar content that comes in with these dark matter subhalos? So we know there's a well-known stellar mass-halo mass relation, and it's pretty uncertain at the kind of dwarf mass scale. So this is the mass scale of the fragments that are fallen in the Milky Way. But it's quite uncertain, but what we do know is it's a very steep relation at these mass scales. Unlike the Milky Way, which is at the peak of the stellar mass-halo mass relation, the star formation efficiency is much lower in these dwarf galaxies, and some even, for the tiniest dark matter subhalos, aren't forming stars at all. So as a consequence of this, one thing we do know is that the progenitors that contribute to the stellar mass of our halo are very different to what contributes to the dark matter mass. And in fact, it's only typically about 1 to 2 of these dark matter halos really contribute a lot of stars to our stellar halo. So we often say the stellar halo can be dominated by only a few massive events, which is very different to the dark matter. If you like, what we're doing is you suppress the contribution from these very low mass dark matter subhalos because they have very few stars or some don't have any stars at all. So this is a prediction, right? This is just a theoretical prediction of what we should expect for our own Milky Way mass halo. But if you think that maybe 1 or 2 things dominate, the question is, why don't we know what these are? Okay, where are they? It should be quite obvious if one thing dominates all the stellar halo mass around us. And in fact, we've had observational evidence for a long time that this is the case in our own Milky Way halo. So probably the simplest measure you can possibly do in the stellar halo is to simply count stars as a function of radius, okay? What are the number counts as you go out in distance from our galaxy? And what was recognized a fairly long time ago now was that if you go beyond about 20 or 30 kiloparsecs in our galaxy, the number counts fall off quite dramatically. And we have what we often call a broken profile. And we can actually relate this to the assembly history of our galaxy. And in fact, something that we inferred is that these broken profiles, so this kind of change in profile at a particular radius, is often built from being dominated by one massive radial merger that really dominates all the stellar mass, at least in the inner halo, and we can kind of naturally get this broken profile, okay? So it's actually been seen for a long time that this could be the case in our own galaxy. There's also been other evidence from either chemistry or kinematics that suggests this is really the case. So massive early progenitors are what dominate at least the inner halo of our galaxy. But it really took until the Gaia mission for us to really say this with some sort of clarity and for people to really believe this picture, okay? So one of the biggest, if not the biggest, discoveries in galactic archaeology from the well-known Gaia mission was the Gaia sausage event, which we now know if we look at the debris or the halo stars in our local solar neighborhood, the majority of them are coming from one particular progenitor, which has been called the Gaia sausage Enceladus, based on the people who discovered it. And what we know, these stars are very radial anisotropy. Their orbits are very radial, so they get taken out to the far reaches of the halo. They're fairly metal rich, which also suggests they're massive. And this is what we think is the main component, if you like, of the interstellar halo. Okay, so this is one of the big discoveries from Gaia. And what we know is that this is a head-on collision with a massive dwarf. And this is the thing that we now, or most people now all believe is true. Oops. So this Gaia sausage, or Gaia Enceladus, is now a field of its own. Okay, since its discovery from Gaia, there have been a ton of papers written about this particular event. It's like the Sagittarius stream, like the LMC, if you like. It's its own subfield of galactic archaeology, which is kind of taken over in this field. Okay, so we know this massive event is critical for the formation of our galaxy, and we know that it dominates what we call the stellar halo. Okay, but what about everything else? Right? We think this one massive thing at least dominates the inner halo. But what about what we want to do in galactic archaeology is not just know about this one thing. We want to know about all the little things that have ever fallen into our galaxy over time. So one way that we can do this, particularly in the era of Gaia, is looking, for example, in energy, angular momentum space. These are conserved quantities, or at least to first order conserved, and look for kind of clumping in these spaces to tell us about individual accretion events that have come in. Now on the left here, this is data, and the right is some labeling of what different structures could be, okay? And I think you can probably all see quite clearly something like the Gaia sausage. It's a very radial component. It sticks out visibly. We don't need to do anything to tell us that this is there. You could maybe say the same for Sagittarius. Of course, we already know the Sagittarius stream exists. Everything else, unless it's like in the disk, is very difficult to do, at least visibly by eye. Okay, so we have to actually work a lot harder to uncover all the other little fragments, particularly because everything is so dominated by these massive accretion events. And in fact, if you count up all the stars in the halo, you can account for most of them either from the Gaia sausage or from the Sagittarius stream, okay? Which in many ways is a positive. Maybe we have actually discovered everything that matters in our Milky Way in terms of its assembly history, at least in terms of mass. But on a more negative point, it makes it a lot harder for us to find all these little things which are kind of hidden underneath all the mass distribution of these more massive things. So one thing we want to do is be able to uncover all of the things that have been accreted. So one step that we've taken in order to do this a bit more quantitatively, rather than just say this is this object, this is that object, is Sergei Kopasov and I came up with this method last year to actually use the metallicity distribution of halo stars to uncover all the progenitors that have made it today. So this relies on the well-known fact that there's a very well-known mass metallicity relation, and this extends down to the dwarf galaxy regime. And if you think that the stellar halo is just a composition of lots of things over time which have their own metallicity distribution function, then you can just model it as just a mixture of a lot of metallicity distribution functions which follow this well-known mass metallicity relation. So the lower mass things have a slightly metal poorer average than the higher mass things, okay? That's the very simple principle that we came up with. So it's essentially Gaussian mixture, okay? It's just a mixture of little contributions to the overall distribution. So that was our idea that we did, and it's, I'm going to skip over the details of exactly how this was applied, but suffice to say, it's a very simple model in the sense that it just assumes that you follow a mass metallicity relation, okay? And we came up with this method, and again, it was just using metallicity data, and we tested it on cosmological simulations, which is quite a big step because there's a lot that can go wrong if you just put it straight on a cosmological simulation. There's a lot of systematics to deal with. And what we found is we could get the numbers, so the number of accreted or destroyed dwarfs as a function of luminosity, relatively well, to within a factor of 2, just using this method. Now, I'm aware that there are people in the audience who work on cosmology, precision cosmology, who would not think a factor of 2 is that great. So I understand that. But when you don't know anything at all, a factor of 2 is not bad. So we were actually super happy about this. And Sergei was also happy about this, which is an even bigger investment, okay? So we could do this with a factor of 2, which was very encouraging. It encouraged us enough to apply it to some data. Okay, so this is what we came up with. This is a luminosity function, if you like, at these colored bits of destroyed dwarfs, okay? For comparison, this purple line here, this is the satellite dwarf luminosity function. Okay, so there is a lot of caveats in this. Okay, there's a lot of things I haven't discussed that can go wrong, a lot of things that we need to think about in more detail. But the fact that we actually have a measurement of this now is very encouraging. There are lots of things that we need to look at in more detail, but this is our first step towards quantifying everything that has ever fallen into the Milky Way. Now, something that's kind of a bit demoralizing, though, is that we've only used metallicity data. And like in the era of Gaia, only using metallicity and not using any of the amazing astrometry or kinematic data seems like something that we should be doing. So we also need to move forward in terms of using this dynamical data. So an example of where this can be done, it's an example that Tom Callan did a couple of years ago based on for globular clusters. Again, this energy angular momentum space, where actually quantified groupings of globular clusters in these spaces, rather than just drawing circles around it or drawing boxes, actually statistically said these globulars belong to these different accretion events. So this is the sort of thing we need to go to more with the stellar halo stars as well, which I think can be done. But ultimately, what we really want to do is use both of these approaches. We want to use something quantitative with the dynamical data. We want to use the chemical data as well, and combine these different approaches to get our destroyed dwarfs luminosity function. And this is where we'll be going. I think we have the tools. We certainly have the data to do this in the coming years. So to end, I just want to come back to the idea of why do we want this measurement? I've said galactic archaeologists really want to know all the little things that have come into the Milky Way over time. But why fundamentally do we care about the luminosity function of destroyed dwarfs? Well, it's worth remembering that we care a lot about the luminosity function of surviving dwarfs. In fact, the satellite luminosity function is probably one of the pillars of near-field cosmology that we've studied for decades. Okay? And we've examined how many small mass satellites we have in the Milky Way and used that to tell us about things like reionization, the nature of dark matter. Okay? So it's been seen as a real fundamental measurement. But to end, I just want to say that if you consider the surviving dwarfs, okay, it's a bit easier than it is to tell you something about the destroyed dwarfs. But together, these are much more powerful. Okay, and to illustrate this, this is number counts as a function of stellar mass, so similar to luminosity function. This is from a numerical simulation. It's actually a hydro simulation. So on the left, you have the surviving dwarfs. This is your satellites. The middle is the destroyed, and the last panel is the combination of the two. So there's two things to note. One is that there's a lot more scatter when you split up the survivor and destroyed. So each little narrow line is just an individual halo, and the thicker line is the average. Okay, the scatter it's a lot tighter when you combine them as a prediction. And also, whether it's survived or destroyed in a simulation depends on the resolution of the simulations, okay? So the two different lines, you've got two different resolution simulations, okay? When you combine these together, the resolution doesn't matter so much. Because the real hard thing to do, both numerically and actually observationally sometimes, is say, is something destroyed or is it surviving? And if we didn't have to worry about that so much, we could have the combination would have a much stronger theoretical prediction, okay? And people are working really hard to try and understand when a subhalo, even dark matter, even forgetting about stars, when it is actually destroyed. So if we want an actual very strong theoretical prediction with our observations, a combined one would be much better. Okay, so to summarize, these fragments that fall into our galaxy, they are linked to key questions, right, in near-field cosmology and galaxy formation. We've been using the surviving dwarf luminosity function for years. I think we're now moving into a regime we could actually add in the destroyed dwarfs as well. It's going to take a lot of work, but it could be very compelling. And I think this is something that we'll move towards in the coming years. And finally, this and lots of other fun stuff is in a review that Vasily and I wrote, which is hopefully is now finished. And it's on the archive, so please take a look if you are interested. Thank you.